We're going to continue our conversation about limits by looking at the laws of limits. Now, some of these we've already done and we've already looked at, but we just didn't give them a formal name. In this lecture, we're going to look at giving them specific definitions. Now, these laws are used for computing limits of functions that are constructed as sums, differences, multiples, products, quotients, and other types of functions. So the first one that I want to do before I get started is I want to establish some rules here. I'm going to assume that the limit as x approaches c of f of x and the same limit as x approaches c for another function g of x exist. So these rules only apply in the circumstances where these two limits exist. If these limits do not exist, I can't use these laws or these rules, and I have to go find other ways in order to determine what the value of a limit is. Now, those three ways are looking at them algebraically, graphically, and then of course we can look at them numerically in a table. So the first one I want to look at is the sum or the difference law. Now this works the same either way for a sum or a difference, so the words sum and difference are interchangeable. Basically, the limit of a sum is the sum of the limits. Now, of course, just like we said, the word sum I could interchange with difference. So this works either way. Okay, so the best way to kind of look at this one is to look at these generic limits that we have up here. So let's look at the limit as x approaches c of f of x plus g of x. Now I have to be careful how I write this. The way I have it written now, I'm just taking the limit of f of x. In order to make sure I'm taking the limit of both, I need to have brackets around here. Well, this is the limit of a sum. What the law says is I can take this and break it up into the sum of the individual limits. So the limit of the sum is the sum of the limits, and this provides that both of these exist. If either one of them fail to exist, do not exist, D and E, then I can't apply the rule anymore. Let's go ahead and look at another problem for this same law, but let's put some numbers to it. Let's look at the limit as x approaches 2 of x squared plus x. So this is the limit of a sum, and I guess I could make this a difference just to show that the difference works here as well. And so I'd split this up into the limit of the difference is the difference of the limits. And I already have the minus sign here, so I make sure I don't include it over here. Okay, so go ahead and evaluate the limits. I'd plug a 2 in. 2 squared is 4, minus, plug the 2 into the x, and I get 2, and 4 minus 2 is 2. So 2 is my solution. Now we were already doing these in our last section, so some of these won't come as a surprise. We're just going to formalize the rules here. Second law, and actually it's going to be the third because there's a law for the sum and there's a law for the difference. So let's go ahead and look at the next one. This is called the constant multiple law. Now for the constant multiple law, basically what we have here is you can pull any coefficient, that's like a number, outside the limit. You can just pull it out front. So any coefficients, and again a coefficient is a numerical value in front of a variable. So any coefficients can be pulled out front. So the way that this one would look, if I had a limit, let's say as x approaches c, and k is my coefficient here, so k f of x, that is just going to equal to k times the limit as x approaches c of f of x. So I can just take that coefficient out front. Now when we actually put some numbers to this, we can see that it's actually pretty straightforward and easy to do. And in fact, we've done these before in previous sections. Let's go ahead and look at the limit as x approaches 4, we'll say, of 3x. I can rewrite this as 3 times the limit as x approaches 4 of x. Drag the 3 along, and of course the limit as x approaches 4 as x, I can plug directly in as 4, and 3 times 4 is 12. So a lot of these make perfect sense. So that's the constant multiple law. We also have the product law and a quotient law, so let's look at the product law first. Now remember, we're assuming that these limits exist in order for them to work. So my third one here is the product law. In this one, the saying for it is the limit of a product is the product of the limits. So if we looked at an example here, using our variables, we could say the limit as x approaches c of f of x times g of x. So this is the limit of a product. I can rewrite this as the product of the limits. So I can just break these up into two pieces. Now each of these is looked at individually, and I'd find the limit of each piece and then multiply. Okay, let's go ahead and put some numbers to this. Let's look at the limit as x approaches, let's say 3 of x cubed times the square root of x minus 2. So I can rewrite this as the limit of each piece. Now in reality, when you're working this problem, you would have plugged directly in and not even worried about these limit rules, but I just want you to see how and why that plugging directly in actually works. So if I plug 3 directly in, 3 cubed is 27. If I plug 3 directly into this piece, 3 minus 2 is 1, and the square root of 1 is 1, so I get 27 here for my solution. So these are pretty familiar, basically plugging directly in. The only thing we need to watch out for is to make sure that the limits actually exist. If the limits don't exist, then I have a problem. Let's go ahead and look at the quotient law. And so for here, I'd say the limit of a quotient is the quotient of the limits. So let's look at an example here. We could look at the limit as x approaches c of f of x over g of x. And so I could split this up into two pieces. The limit as x approaches c of the numerator over the limit as x approaches c of the denominator. Now one thing I have to realize here, provided both limits exist, and the limit as x approaches c of g of x cannot equal 0. Now the reason we say that is the denominator can't be 0. Okay, we've already worked with that situation. So the limit has to exist, and the denominator, the limit in the denominator cannot equal 0. And the limit has to exist for all of these examples, but it seems like with the quotient rules where that actually comes up most often. Let's go ahead and look at an example with some numbers in it. That's always helpful for me to see those. Let's look at the limit as x approaches 4 of the square root of x over x squared minus 2. So the limit of this quotient is a quotient of the limits. So let's go ahead and plug the 4 directly in. The square root of 4 is 2. And if I plug 4 directly in down here, 4 squared is 16. 16 minus 2 is 14. And this reduces to 1/7. So again, provided that that limit exists. Now there's some other laws too. Let's go ahead and look at those real quick. And these laws help you work with exponents. So this one we could call the power law. So for the power law, we would say the limit of a power is the power of the limits. The limit of a power is the power of the limit. Now we can combine these laws. I can have an addition, a subtraction, a power, all sorts of different things. And so it's important to be able to distinguish between them. So for an example here, in the generic sense, we could look at the limit as x approaches c of f of x, and this f of x, let's say, is raised to the power of n. So what this law is saying is, you know what? I can go ahead and take the limit of the inside, and then when I find that solution, raise the whole thing to the nth power. So the limit of a power is the power of the limit. Let's put some numbers to this as well. Let's look at the limit as, let's say, x approaches 4 of x squared minus 3 to the 4th. So we can rewrite this. This would be the limit as x approaches 4 of x squared minus 3. Okay, and then we'd raise this all to the 4th power. So I do one step at a time. So the first step would be going ahead to take care of the limit first. And as we take care of that limit, I can see that I have, as x approaches 4, so I plug a 4 directly in. 4 squared is 16. 16 minus 3 is 13. So I'm left with 13 to the 4th. And 13 to the 4th would be 28,561. It's amazing. Exponential growth there. So again, the limit of a power is the power of the limits. Now, if this exponent had been like an n over 4 or something like that, what ends up happening is I should be able to find the root and the power. So there's another one here called the fractional power law. So the fractional power law works just the same. So I'll call this one the power or fractional power. And I'm going to add one more to the list. This is going to be called, I guess, something about a, not a constant multiple, but this is just about a constant. And this says the limit of a constant is the constant itself. And sometimes this one's a little bit hard to explain, so we might look at this graphically as we go through and try and justify this. Okay, here we go. So if I was trying to find the limit as, let's say, x approaches 2 of 7, the answer is 7. So why is that? Why is it that constant? Well, let's go ahead and graph this. So on our x-axis, we can see that we're approaching 2. So here's 2 on our x-axis. Now, what is 7? What does that mean? Well, this basically means y equals 7. So if I were to graph this, it would equal y equals 7. So we'll say this is y equals 7. Now remember, when we're doing limits that we learned from our last lesson, am I taking my limit as x approaches 2? I'm approaching from the right, and I'm approaching from the left. So the limit as x approaches 2 from the right of 7 equals 7. The limit as x approaches 2 from the left of 7 equals, the limiting value is 7. Because the limit from the left and the limit from the right are equal, the overall limit agrees at that value, so the limit as x approaches 2 of 7 is 7. So I can look at that graphically. I could also look at it numerically as well. So those are some of the limit laws that we're going to be using to evaluate limits. And again, we've already used quite a few of them in previous sections, but we're just formalizing them here. Now let's go ahead and look at an example where we're calculating a limit. Now the first thing you should do when you're looking at limits is just go ahead and plug the number in and see what happens. If something good happens, then what happens is you're done. If you get an undefined or an indeterminate form, then you have to do something else. So this looks like to me it's definitely a limit of a quotient. So this is the quotient law. So this means I can take the limit of the top and the bottom, and then let's see what happens. Well, what happens here is I have a problem. When I plug 0 in here, I get 1 over 0, which is undefined. And if this is undefined, that means the limit does not exist. So if the limit does not exist, and I have another problem down here, is I have a 0 as well, but the top part is the bad thing here. So because the limit doesn't exist, the limit quotient rule cannot be applied that we just learned above. So that means I'm going to have to come up with some other way to evaluate this limit. So I could look at this graphically, I could look at it numerically. I think I'll have a look at this one algebraically. So let's look at the limit as x approaches 0 of 1 over x all over x. I'm going to rewrite this. So I have 1 over x, and I'm dividing it by x. Now remember, when you divide by a fraction, you multiply by the reciprocal of the second fraction. So this is really x over 1. And so when I flip it, the division changes to multiplication. I'm left with 1 over x. I end up with the limit as x approaches 0 of 1 over x squared. So that's my new limit that I'm working with. Now when I plug 0 directly in, I get 1 over 0, which is undefined, and therefore the limit does not exist. Now we've looked at this one before. I know the limit doesn't exist, but I would like a little bit more information about why it doesn't exist. This is the graph of 1 over x squared. This is a graph that you should know. And as we see, the limit from the right is equal to infinity, the limit from the left is equal to infinity, so the overall limit at 0 looks like it is approaching infinity, but a limiting value of infinity is no limiting value at all, so that's why the overall limit doesn't exist. So the limit as x approaches 0 from the left equals the limit as x approaches 0. I think I want to write that differently. We wrote it different in our other lecture, and I want to be consistent. So the limit as x approaches 0 from the left of 1 over x squared is infinity. The limit as x approaches 0 from the right of 1 over x squared equals infinity. And these are equal. So that tells me the overall limit then is also approaching infinity, and therefore the limit does not exist. And the reason I say that is there is no limit because it's going toward infinity. So let's go ahead and just look through quite a few limits and practice taking limits. Now each of the problems we're going to be looking at will be slightly different to kind of show a different skill you might want to have when you're trying to find limits. Let's go ahead and look at the limit as x approaches negative 13 of x squared minus 169 all over x plus 13. Now if I plug negative 13 directly in, negative 13 times negative 13 is 169 minus 169 is 0. Negative 13 plus 13 in the denominator is 0. 0 over 0 is indeterminate. Now remember, what indeterminate means from a previous lecture is to do more work. Now the do more work that we could do is numerical, algebraic. We could also look at this graphically. I think we'll just look at this algebraically. I like this problem because x squared minus 169 is the difference of perfect squares. So we want to try and basically cancel out this denominator because it's the 0 in the denominator that's causing me trouble. So the numerator factors into x plus 13, x minus 13. And then we can see that we have canceling occurring here. So the x plus 13's cancel. And so I'm just left with the limit as x approaches negative 13 of x minus 13. If I plug directly in, I get negative 13 minus 13, or a negative 26. So that's my limit. I've evaluated my limit because I was able to simplify it. One thing I want you to keep in mind here, there's a restriction. Even after I've simplified it, I need to keep in mind that x cannot equal negative 13 because that was the restriction from my domain before I canceled it. So make sure that you're keeping an eye on that because it is an important restriction to remember. Now even though x cannot equal negative 13, this is saying it is approaching negative 13. So I can look at its behavior as it approaches negative 13. So being able to factor is going to be really important. So algebra is a big deal here. Another example, let's look at the limit as h approaches 0. I think back when you were working on some of these algebra homeworks for the review part of the class, you did some simplifications on some problems similar to these. And those were to kind of prepare you to work with these. So as usual, the first thing we do is we plug directly in. As h goes to 0, I'm left with 5/7 minus 5/7 all over 0. So I get 0 over 0, which is indeterminate. And of course, indeterminate means to do more work. Well, the more work I want to do here is to simplify this, get rid of the layered fractions. So let's look at the limit as h approaches 0 of 5 over 7 plus h minus 5/7. So it'll be all of this divided by h. And I'm going to rewrite that as h over 1. So let's go ahead and look at the limit. Now I didn't specifically say so, but up here in the top I did use the limit laws. I used the limit over here of the numerator, so the limit of the quotient is the quotient of the limits. I actually went through to evaluate that and it didn't work out because I got an indeterminate form. So here I'm going to find a common denominator. So here I multiply top and bottom by 7. And here I'll multiply top and bottom by 7 plus h. Okay, so this is going to look like the limit as h approaches 0 of 7 times 5 is 35 minus 5 times 7 plus h all over 7 times 7 plus h. And this is divided by h, which is the same as multiplying by the reciprocal of 1 over h. So I have the limit as h approaches 0. I have 35 minus 35 minus 7, whoops, not minus 7, but minus 5h. Now this will be some place that you'll want to always be very careful about. Make sure you take the negative and the 5 and distribute it to the h. I'm going to combine the h over here now, 7h times 7 plus h, and keep simplifying. So the statistical, or not the statistical, but the calculus concepts here are just the very end. We're just doing a lot of algebra so far. So 35 minus 35, of course, is 0. And so I have canceling occur with the h's. So I'm left with a limit as h approaches 0 of negative 5 over 7 times 7 plus h. I'm finally ready to take the limit. And as I do this, this h goes to 0. And I'm left with limit, I'm sorry, I already took the limit because the h went to 0. I'm left with negative 5 over 7 times 7 is 49. So quite a bit of work to do there. The first thing you should always try to do first, of course, is to plug directly in. And if things work out when you plug directly in, then you don't need to waste a lot of time with lots of other methods. Sometimes you'll have to look at different techniques when you're working with the problem, so I want to make sure you see several of these techniques. And all of them are some sort of an algebraic technique. Let's look at the limit as h approaches 0 of the square root of 361 plus h minus 19 all over h. So as usual, we'll just take the limit directly. We'll use the quotient law. The limit of the quotient is the quotient of the limits. I'll go ahead and take the limit of the numerator and the limit of the denominator. The square root of 361 plus 0, that's just the square root of 361, which happens to be 19. 19 minus 19 is 0. 0 over 0 is indeterminate. And of course we know indeterminate means do more work. And the work we're going to do on this one is algebraic. Now I notice I have a radical involved here, and when I have a radical, a lot of times I like to be able to multiply by the conjugate. Now a lot of times we're used to multiplying by the conjugate of the denominator, but this time we're going to be looking at the conjugate of the numerator, so this is a little bit different. So limit as h approaches 0, so 361 plus h minus 19 all over h. Now the conjugate that I'm referring to would be the square root of 361 plus h plus 19. So the conjugate means the exact same terms that only differ by the sign in the middle, positive to negative or negative to positive. But whatever you do to the top, you have to do to the bottom. So basically what I've done here is I've multiplied by 1 because this would reduce itself to 1. Now the reason that we choose this is when I multiply by the conjugate and I'm multiplying everything in the numerator, the radicals will end up going away in the numerator. So let's look to see what we have. The limit as h approaches 0. I'm going to FOIL this out. Root 361 plus h times root 361 plus h is 361 plus h, plus 19 root 361 plus h minus 19 root 361 plus h, and then minus 19 times 19 is 361. And this is all over h times the quantity. Now a lot of things will cancel here. So the 361s cancel, that's good. These cancel, positive 19 root and negative 19 root. And it looks like to me the only thing I'm left with then is h. So I have an h in the numerator and an h in the denominator. So these h's cancel, leaves me with the 1 in the numerator, and I still haven't taken the limit yet, but this is the limit as h approaches 0 of 1 over root 361 plus h plus 19. Now, as h goes to 0, this just turns out to be the square root of 361. The square root of 361 is 19, so I have 1 over 19 plus 19, which is going to be 1 over 38. So really, the calculus part, the limit part, is just at the very end, a little bit here at the beginning, but most of this is just simplifying things algebraically. So strong algebraic skills are important. Now this idea of multiplying by the conjugate works not only for the numerator but for the denominator as well. So if you run across any problems where it might be helpful in the denominator, make sure you try that as well. We're going to look at the Squeeze Theorem next. Now the Squeeze Theorem is also called the Sandwich Theorem. There could be some other names for it too, but the Squeeze Theorem or the Sandwich Theorem are probably what you hear about most commonly. So the Squeeze Theorem might look at an expression like the limit as x approaches 0. 0 is in radians here of x sine 7 over x. Now if we plug directly in like we usually try to do, the limit of a product is the product of the limits. The limit as x approaches 0 of x is 0. And then I end up with this sine of 7 over 0. 7 over 0 is indeterminate. It does not exist. This is not a limit kind of an idea here. I can't take the sine of something that does not exist or is that undefined, I guess I should say. Let's keep with undefined here. So the sine of the undefined angle, I can't do anything with. So this entire limit, 0 times the sine of something that's undefined, I can't do anything with. I can't say that it doesn't exist. I can't say that it's necessarily indeterminate, but I do need to do more work here. The indeterminate forms we have are 0 over 0, infinity over infinity, which we haven't got to yet, and a couple of other forms. But for this one right now, we just have to do some more work. So the Squeeze Theorem basically says if I could find something above or always higher than this theorem or this function and always lower than, and the limits are the same values, what I could do then is come up with the overall limit of the middle. So let's go ahead and graph x sine 7 over x. So here's my calculator. And let's go ahead and graph y equal, here we have x sine 7 over x. Now make sure you're in radian mode if you're not already sure about that, and let's hit graph. You may need to readjust your window, and that would be right here. You could click window and readjust your window if you needed to. So here's our graph. Kind of a Batman looking thing. Let's go ahead and snap that into our lecture. So with this graph, I want to figure out what's going on as x approaches 0. And as you can see here, the behavior of this function is it's starting to oscillate as it gets closer and closer to 0. And I really don't know what's going on right at 0. So the Squeeze Theorem says if I can find a function that's always above the function and one that's always below the function, then what ends up happening is if I can find the limit of the one that's always above and the one that's always below, and those limiting values are the same, then this function is squeezed in between those, and I can estimate that limit as well. So one way what we could work with this, let's think about x sine of x. Actually, let's just think about the sign right now. The sign of any function is always going to be between -1 and 1. So this would be thinking about from -1 to +1. So I'm trying to figure out or design something here. Now over here, I could multiply by x, and then maintaining that inequality, I could make this a -1 times x would be a -x. And over here, a 1 times x would be a +x. So I'm trying to sandwich this in between and verify this inequality. So again, it has to be between these two values. So I'm getting kind of close here. Sine is always between -1 and 1, remember. And then I multiplied through by x, but this doesn't quite do the job. If I graph -x, it would look like this. It would come through here, which is always above, but then it strikes through and moves below. And then the graph of x would be up through here. And this actually looks like a pretty good graph, but I can't have this function drop below. It always has to be below, or it always has to be above, and this one runs above and then below. So I think what I'm going to do here to fix this, I'm just going to look at the top piece here. This top piece is an absolute value graph. So I'm going to call this minus absolute value of x and positive absolute value of x. Now when I graph the absolute value parts, I'll sketch them back in. It'll end up looking like the same graph. This is an absolute value function, and this is an absolute value function. So this purple graph is equal to the absolute value of x. This green graph is equal to minus absolute value of x. So we can see that this graph of the x sine 7 over x is always in between. So what I do next is I take the limit of each of the graphs that I came up with. So I'm going to take the limit as x approaches 0 of a negative absolute value of x. I can plug 0 directly in. The absolute value of 0 is 0, and of course -0 is just 0. Then I'll take the limit of the other side, absolute value, and I get 0. And because I've shown that my function of interest, x sine 7 over x, is always between these two values, this works really well then, because the limit of the above function and the below function are the same, so the limit of the function in between then has to also be the same. And in this case, it's going to be 0. So this is the squeeze theorem, because that theorem says that this function that's always in the middle gets squeezed. Now, not very often will you be asked to come up with these values that squeeze, because it could take a long time to come up with correct values. Usually you'll be given these and then asked to establish that. Now I wouldn't expect that you would know what that graph looked like, the sine of 7 over x, but the absolute values, you should probably know those. So let's go ahead and graph the absolute values and see how those look. Math, the absolute values I think are under number, so we have this ABS, absolute value of x. And then I have negative, let's go into math again, over absolute value of x. And let's see what this looks like when I graph it. Yep, so you can see that it squeezes just like we needed it to the function in the middle. And so the limit of the function above and the limit of the function below are the same. So the overall limit of the function in between has to be the same as well. So the squeeze theorem is pretty neat. You will not be asked to come up with the functions or the graphs that do the squeezing above and below, but you should be able to look at a graph or create your own graph that comes up and shows how the squeeze theorem works. So the squeeze theorem is another tool in our toolbox that we can use to find limits. Now sometimes you'll be given a piecewise function to work with. Now before we were working with piecewise functions, they were also given to us in a graph form, but for this example it is just going to be given to us in functional form. And then we'll be asked to find some of the missing values. So we're given the function g of x equals, let's look at a parabola x squared minus 8x. And this parabola is only defined when x is less than or equal to a negative 1. And let's also look at ax cubed minus 3, and this is only true if x is greater than negative 1. Now what we're asked to do here then is we're asked to find the value of a. So over here in this function a, so we're asked to find the value of a for which the limit as x approaches, let's do negative 1 here, of my function exists. It doesn't say what it has to exist at, it just says that it exists, and if we can actually find the value of the limit. Well, let's think about this. This is a parabola that opens up, and I'm just going to look at a general idea here. So I have some sort of a parabola that opens up. Now this third degree polynomial, it probably looks something like this, or like this, depending on whether a is positive or negative. But if this is the point negative 1, and again this is just a very, very general graph, I'm just kind of thinking about some things here. If I want this limit to exist here at negative 1, what has to happen is this graph, I'll put it in purple, has to approach the same from the right as it does from the left. So as I approach from the right, my limiting value has to be the same for my function that I approach from the left. So the greater than negative 1, actually let's rewrite this. This is for x less than or equal to a negative 1. So let's put, and it doesn't matter, the same logic holds, but just to kind of clarify what these graphs look like. So this is a parabola opening up for x less than or equal to negative 1, and then for x greater than negative 1, I need to have this function defined. Well, let's think about that. If that function looks something like this, the limit wouldn't exist because the limit from the right would be different than the limit from the left. So it can't be here, and it can't be anywhere down here for the same reason. The limit from the left wouldn't equal the limit from the right. So to make this work, somehow the limit from the right has to equal this exact same point. Now it might be a hollow point on top of that filled point, it doesn't really matter, but the graph's going to have the same limiting value on either side. So let's look at x squared minus 8x, and let's go ahead and look at the limit of just that piece. If I plug a negative 1 in here, that's negative 1 quantity squared. Make sure you put parentheses around the negative 1 or you'll get the incorrect answer here. This would be 1 plus 8 or 9. So this limiting value here is 9. This picture is not accurate. It's just kind of to show us the idea that the limit from the left and the right have to be the same. So that tells me that the limit as x approaches negative 1 of my other graph, the ax cubed minus 3, that also has to equal 9. Okay? So I don't know what a is, but I know if I plug a negative 1 in, I get a times negative 1 cubed minus 3. Negative 1 cubed is a negative 1 times a is negative a. And then I will add 3 to both sides and I get negative a equals 12 or a equal negative 12. So the value of a equal negative 12 makes this limit exist. Now I'm going to graph this because I want to know if this worked. So we decided negative 12. Now how can we graph a piecewise function? Okay, so let's go ahead and grab our calculators and let's clear everything out of the y equal. I'm going to graph a piecewise function. Now graphing a piecewise function is a bit tricky. There's just some commands you need to remember, and if you can't remember them and you need them, Google them or go back and try and find the video. Or go back and try and find the directions in this video. So when you're graphing a piecewise function, the first thing you need to do is everything has to be in parentheses because you have to define what exactly is going on with your function and with its domain or its restriction. So let's go ahead and enter x squared minus 8x. So x squared minus 8x. And then we're going to close parenthesis and then open parenthesis for the test part of this. This is the restriction. So this would be x less than or equal to a negative 1. So x. Now the less than or equal to would be under this test option right here. So that would be second test. And there's my less than or equal to on the very bottom here. So less than or equal to, and then -1. Then I'll close parenthesis, and I'm going to put in a plus, not because I'm adding something, but because I'm adding another entire function here. Now we decided that our next entire function was -12x cubed. Okay, -3. Close parenthesis, open parenthesis for the test. This is x greater than -1. So that's under the test, x greater than, that's the third option here down, greater than -1, close parenthesis. Let's graph. Now one thing that we have as a limitation with this is we don't know exactly what's going to be going on with the holes in the graph and the hollow points, because this doesn't give us that. This graph doesn't quite look right. Let me see if I can go fix it up. So to fix this, I went back to the window and I just expanded my Y max up a little bit so I can get more of an idea what's going on. And now this looks right. So what was happening before is it looked like we could only see one part of the graph. And there's a little bit more going on here now. So let's go ahead and look at this in terms of the problem that we just have and see if I can figure out something about the limits. So what we have going on here is this top part of the graph right up to here. This is x squared minus 8x. Now the bottom part of this graph below this point, this is the -12x cubed minus 3. And what we can see here then is the limit from the right does equal the limit from the left, so the overall limit does exist. So let's go ahead and officially write that out. The limit as x approaches -1 of g of x. Let's approach it from the left. And if I approach it from the left, I'm plugging into x squared minus 8x. And you can see here that I'd get 1 plus 8, or 9. Let's go ahead and approach it from the right. Limit as x approaches -1 from the right of g of x. I would plug into the -12 times -1 cubed minus 3. So that would give me a -1 times -12 is 12. 12 minus 9 is 3. So the limit from the left and the limit from the right are the same. Therefore, I could say the overall limit as x approaches 1 of my function exists, and we know it's 9. So we have two things here. I could find the value of a that made this true, and I could also find the actual limit. Now you don't have to have a graphing calculator to help you do this. It does help to see the visualization of it. You can see up here my curve that I was visualizing wasn't very accurate, but it gave me the idea of what had to happen. The limit from the left and the limit from the right had to be the same. So if you follow the rules of the limits using the limit laws, which, you know, we actually use a lot of those limit laws without even thinking about it. We just plug directly in. You should be fine plugging in first, getting an answer. If you don't get an answer and you get an indeterminate form, you need to try some more techniques, algebraically probably. And then, of course, with the squeeze theorem, we learned that we are usually given the functions to squeeze the function with. And then we just needed to establish that that particular statement was true, and then also apply the squeeze theorem and do some graphing. Now on an exam, you're not going to have a graphing calculator. You won't have a calculator at all. So how would I test on the squeeze theorem or something? I would provide the picture, or I would provide the functions for you and ask you to run the squeeze theorem on them. As usual, if you have questions, please let me know. You can take a screenshot and email me, or even better would be to take a shot with your camera of your work and send me your questions, and I'm happy to reply back and help you. You also have the option of the Pearson Connect to a Tutor, and if you haven't tried that yet, please do so as soon as possible so you know how to use that feature. And it's also an assignment as well, so make sure you check out the Getting Started page for some more information on that. Good luck, and again, if you have any questions, please let me know.